Hey guys, this is Mr. Bennett, and this is the Unit 8 review for the exam. Normally we do a think binder or something like that, but this time around that's not going to work. So here we go. Let's look at question number 1. Question number 1 says, all atoms want to be stable. What do they need to become stable? This is kind of a review question. So hopefully when you see the word stable, the word that comes to mind is octet. We know that they need 8 valence electrons, also known as an octet. Okay, now the thing I want you to think of next is the fact that, and this comes off of this idea, is that not all atoms are going to get to their octet or their valence electrons the same way. So for example, they may get there by gaining or losing electrons. If that's the case, then they're going to get to their octet by forming an ion. They also might get there by sharing electrons. Okay, and if they're going to do that, then they're going to get to their octet by forming a covalent bond. So the point is that both of these things, whether it's an ionic bond or it's a covalent bond, they're both achieving the same goal. Whoa. Bond. There we go. They're both achieving the same goal. And that goal is, in both cases, to get the atom involved, its octet. Okay, that's the goal. So moving on to question 2, it says this goal is related to electronegativity. Compare the electronegativities of fluorine and sodium. How and why are they different? So if we just look at the periodic table, okay, so if I draw my little periodic table drawing here, okay, drop those in there, just to kind of think about their locations. Sodium is over here and fluorine is over here. So based on electronegativity increases going up and to the right. Okay, so it says the goals related to electronegativity. Compare the electronegativities of fluorine and sodium. How and why are they different? Okay, so fluorine is over here, sodium is right here. So we would say that fluorine has a greater electronegativity than sodium. Okay, and the why has to do with the fact that fluorine is much closer to its octet. Okay, it only needs one more electron to get over here. Okay, another way of thinking of it is its valence electrons are a lot closer to the nucleus, so the nucleus has more pull on those electrons. Sodium, on the other hand, it would have to gain a full 7 electrons to get to this octet. Instead, it's much easier and much more efficient for it to just lose an electron and look like a noble gas. So its electronegativity can be low because it's not really invested in keeping that electron. It would actually become more stable by losing that electron and becoming like a noble gas. Okay, so the how, or I guess, how are they different? Fluorine is greater than sodium, and the why you could explain in 2 ways. It's much easier for this to lose its electron, so it's not invested, it's not holding on to its electron as tightly. That would be the sodium. And then fluorine, it basically only needs one more electron, so gaining 1 electron will get it a lot of stability. And if the goal is stability, right, getting to stability is going to be worth a lot to that atom. So this fluorine has a lot of encouragement to get its octet by gaining 1 electron. So it really wants to pull on electrons. It has a great pull. Sodium, on the other hand, has very little invested on gaining electrons. In fact, it wants to lose electrons, so therefore it's not really going to have a pull on electrons at all. Okay? All right. Number 3. If 2 atoms' electronegativities differ by 1.7 or more, the bond between them is, okay, so we're saying that their difference is greater than 1.7. Therefore, the bond between them is ionic. Okay, you got to remember that scale. The scale goes from 0 to 0.5 to 1.7. And if it's in this range, it's nonpolar. If it's in this range, it's polar. And if it's in this range, it's ionic. So the next part of the question says, explain how both atoms achieve stability and the bond is created. So we're talking ionic. Okay, so the first thing is you've got a metal bonded to a nonmetal. Okay, And the way this is going to work is this metal is going to lose an electron, and then that electron is then going to be added to our nonmetal, which is going to gain an electron. So long story short, the electron is transferred from the metal to the nonmetal, okay, to get them their octets. Okay, so metal loses the electron, which will drop it back into the noble gas configuration, and the nonmetal will pick up the electron, gaining. Once you have that, okay, once you've transferred that electron, you then have a positive attracted to, like a cation, attracted to a negative ion through electrostatic attraction. And that's your ionic bond. Okay, so that's question 3. Let's move on here. I'm going to erase this. So if you need to still write this down or you're still trying to hear it, you can back it up or you can pause it. But I'm going to erase this and move this up slightly so we can get to question 4. Okay, so question 4 says, illustrate this bond by choosing an element to bond with nitrogen. Use Lewis dot structures and arrows to show the movement of electrons. Okay, so I'm going to pick an easy one just to make this kind of work nicely. Here we have aluminum. Okay, aluminum has 3 valence electrons, so I draw them in like so. And then we have sodium, or not sodium, sorry, nitrogen. What I'm thinking, nitrogen, which has 5 valence electrons. So we plug those in like so. Okay, and the goal again is to get to an octet. All right, but metals don't get to octets by gaining electrons. They get to an octet by losing electrons. So what we can do here is, sorry, that got shifted, is we can look at our aluminum and it can lose this electron and give it to nitrogen. And it can lose this electron and give it to nitrogen here. And it can lose this one and give it to it here. When that happens, our final kind of configuration is we have our aluminum, which has lost 3 electrons. So overall, it's going to have a charge of positive 3, right? Because it lost 3 electrons, but it still has the same number of protons. Nitrogen, on the other hand, has gained 3 electrons. So nitrogen's Lewis dot is now going to look like a nice, pretty octet, 8 dots. Okay, but it has 3 electrons more than it started with, so its overall charge is going to be negative 3. Okay. Once that happens, we have a positive 3 charge, we have a negative 3 charge. So these guys are going to stick together. Positive charge is going to be attracted to the negative charge, and we're going to get the formula unit ALN. Okay, so we made an ionic compound, and the way that it formed was aluminum gave 3 of its electrons to nitrogen, nitrogen keeps them, becomes an anion of negative 3, and aluminum, having lost its electrons, is now a cation of positive 3. Okay. Now let's move on to question 5. 5 says, if the 2 atoms' electronegativities differ by less than 1.7, the bond between them is covalent. Okay, now keep in mind that covalent could be one of 2 things. It could be nonpolar, or it could be polar. But this dividing line here, 1.7, says that if it's below 1.7, they're sharing in some way. If it's above 1.7, it's what we just talked about, the fact that electrons were transferred. So the next part of the question says, explain how both atoms explain how both atoms achieve stability and the bond is created. So the way they achieve stability, again, stability you should be thinking about octet. Okay, the way that they do this is they're going to share electrons to reach octets. Okay, so one atom will share some of its electrons with another atom, and by sharing multiple electrons, eventually they'll get to 8, however many they need to get to 8, or their octet. So question 6 says, illustrate this bond by choosing an element to bond with nitrogen. Use Lewis dot structures and arrows to show the movement of electrons. Write the formula of the resulting molecule. So first of all, we have our nitrogen with its nice 5 valence electrons. So I'll draw those in. Okay, and then we have to pick something we want to bond it to. Well, this is a covalent, so that means that it's going to have to be a nonmetal bonded to a nonmetal. So if I pick another nonmetal, I'm going to go We'll go easy. Let's go hydrogen. Okay, so a hydrogen has 1 valence electron. Okay, and when we connect this, we're going to share electrons here. Okay, this is going to get hydrogen its octet because hydrogen only needs 2 electrons to get an octet. Okay, so this hydrogen is actually nice and happy now. It is more stable. It's reached its octet. Nitrogen, on the other hand, though, it only has 1, 2, 3, 4, 5, 6 electrons at its disposal, but it wants 8 to get to its octet. So we need to add another hydrogen. Okay, so we add another hydrogen, and when we do that, whoops, sorry about that. Okay, there we go. When we do that, so we connect these two, right? Now, again, the hydrogen's happy because the hydrogen has 2 electrons, which is what it needs for its octet, but the nitrogen is still unhappy. It has 1, 2, 3, 4, 5, 6, 7 electrons. It still needs to get to 8. So we add another hydrogen. Okay, and when we do that, we connect this. Now, nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons at its disposal, so it has its octet. This hydrogen is happy because it has its 2. Okay, so the point is that by sharing, okay, we got the nitrogen to its octet. By adding hydrogens that could share their single electrons, we got to the octet. So the formula for the resulting molecule would be nitrogen bonded to 1, 2, 3 hydrogens, so it's NH3. Cool. All right, let's move on to number 7. And number 7 says there are 2 types of covalent bonds, polar and nonpolar. Explain the difference between them and give an example for each. So a polar is when it's a covalent bond where the sharing is unequal. And we can quantify this, meaning we can give it a number now because we've talked about covalent bonds and polar bonds versus nonpolar bonds. So the difference in electronegativity is greater than 0.5 and less than 1.7. Okay, so an example would be something like we could do carbon to chlorine. Okay, so carbon has an electronegativity of 2. And if we bond it to a chlorine, which has an electronegativity of 3, right, we take the difference. So 3 minus 2 gives us a difference in electronegativity of 1. So this bond is polar, and what's happening here is the electron is favoring chlorine. So it's hanging out on this side of the bond more than it's hanging out on this side of the bond. So the sharing is unequal. Okay. Now for a nonpolar bond, it's still a covalent bond, right? So covalent bond where the sharing is equal. And the difference in electronegativity is less than 0.5. So an excellent example of this would be to take something like chlorine and bond it to another chlorine, in which case the electronegativity would be 3 and 3, so 3 minus 3 gives us 0. And there's plenty of other examples, but the idea is that the electronegativities are so close that they have to share. That each atom's pull on the electrons that are bouncing back and forth here as part of the covalent bond, each atom's pull is essentially equal. So the electron's going to kind of hang out in the middle. It will have equal sharing.